Right, good afternoon. We're going to pick up the pace a little bit. My name's Chris Scott. I have spent the last year looking at topological defects and their relationship to magnetized plasmas with a small team, and I've been doing that for the Air Force. So I think they're extremely relevant to this room, and I want to deliver a theory that I believe is contextual across all the different experiment types. I distributed across the room some notes and pre-reading that is complimentary. If you go to exafuse.com.au and you click on this resources tab, you'll find all of the notes and this presentation there. All right. While you're watching a beautiful U1 cross U1 clump of electromagnetic energy, I will get up the presentation. Oh, stand by. Okay, I want to deliver a contextual framework, as I said. The problem space that we all have is that we've got several different experiment types, and I've loosely categorized them into three different ones: solid state diffusion, magnetized plasmas, and cavitation. And these phenomena are apparent across the whole swath, more or less. This is a very generalized point of view, but the anomalous phenomena include multinuclide transmutations, strange tracks, which you've heard a lot about this morning, lack of nuclear markers. Neutrons are there, sometimes they're not. Question marks over whether they are faux neutrons or real neutrons. There's excess heat and virial coefficient changes being reported, more so recently from the Russian camp. And then I think the last one that is valid to add, at least for solid-state diffusion and magnetized plasmas, is this near IR and IR radiance anomalies. Oh, yeah. Okay, so I mentioned before that we're interested mainly in the realm of magnetized plasmas. So this is where it started for me. I wanted to... It's gone. Let me describe it anyway while it loads. Okay, so we basically took the model of Messiat's for a cold cathode emission, and what this is, so Sventuk is his contemporary, so we have an explosive electron emission which creates a crater, and it also creates a liquid metal jacket that pushes up, and every 5 nanoseconds or so we get a metallic droplet separation, and it's during this droplet separation that we get the repetitive process occur. So what you can see at the top on the left-hand side is you would have, imagine, a macroscopic cathode material droplet there, probably liquid, and it's acting as a current collector. So there is current going through this liquid metal neck. It's increasing in temperature and increasing in current density as the radius reduces. So this is just a reproduction of what Sventuk did. We don't need to go to any kind of kinetic code. We can just have a look at the temporal evolution, noting the electron-electron, ion-electron, and ion-ion collision rates. We can just look at how the temperature for the ion and electron species goes, and basically the end of the story is that you expect to get higher electron temperatures just because the electrons have a higher, they have different Maxwellian relaxation times. Okay, so I've got a really hot state, and what I'm interested in is this transition through the critical state. So I go from a liquid into a plasma. And what you can see, if you just look at the yellow line, that's log current density. We expect on a sub-nanosecond timescale in this model that it will go have a dramatic decrease in the current that's going through there. And that makes sense. It checks with actually exploding wire experiments where they measure the current, the resistivity of the plasma. So we expect to see that this current would decrease going through that critical transition. But that's not what we see. What we actually see, if you look at the IV plot inset, so this is a 10 micron tungsten wire, and we drive this instability, this thermal instability, and what you can see is that instead of going down and to the right, which is where we expect it to go on a 10 nanosecond timescale, we actually increase the current. And you can see on the temporal evolution here on the bottom, if you look at the red, that's our current measurement. There's rise times on the order of probably less than 2 nanoseconds. So what is actually occurring in here? That was the question that we basically were posed with. And instead of going into the kinetic code and basically the latest and greatest plasma simulations, we kind of went a different route, wanting to understand, what is a Fermi fluid going to do under a highly driven thermodynamic state, and B, what does a Fermi fluid condensate look like? We also didn't need to go into a kinetic code because we just have this model where we can understand that there's an unimpeded plasma expansion radially out, but the shock wave that gets propagated back up through the metallic neck is very non-ideal, and the level of ideality goes up with a heavier cathode material, as you can see. Okay, so we ended up having to tackle probably one of the hardest problems that I would consider, turbulence. We absolutely cannot take statistically homogeneous and isotropic assumptions in trying to figure out our regime that we're living in. It's true that highly driven local thermodynamic states, that includes diffusion, cavitation, metallic impact, and shear, are all subject to a 5-dimensional energy surface. That sounds counterintuitive, but here's a more crazy statement that I'm going to make. SO3-1 is the thermodynamic equilibrium representation of SO3-2, the de Sitter space. And it's subject to a scale-dependent thermodynamic Machian threshold. That might sound very scary, and I'm going to do my best to explain why. But firstly, 2 reasons why it's a 5-dimensional energy surface. But also, before I get into the first one, consider that a superconducting model is SO5. So if you're an electron and you're a condensate electron, you live on a 5-dimensional manifold. Okay. The first reason, though, is that Kolmogorov-Arnold-Moser theorem gives us an excellent starting point. In that theorem, in 1957, he says that for a invariant tori, small perturbations exist, but and this is valid for any non-dissipative system with that's involution. So that is non-dissipative and described by a Hamiltonian. So that's essentially our starting point. So we're going to go down to the point where we've got a spin glass picture. So a whole, imagine your metal and you've just got a bunch of oscillators. And what follows from Kolmogorov, his theorem was that for a system with n degrees of freedom, the phase space is free to explore 2 n dimensions, and the energy surface is 2n minus 1 dimensional. The manifold, that phase space is a manifold that is an n torus, and that is the invariant n torus. Okay, he made that he asserted that, but never proved it publicly, or never published his proof. But Hubbard proved it in 2012, and I'd highly recommend going through that. Okay, the second reason, though, is that Dubovik, in his dual potential formalism defines diality. I don't think he was the first one, but his formalism is a neat package for dealing with his 5-dimensional energy surface. And diality is just the dual transformation of both electromagnetic sources and fields. And it makes complete sense in a fluid dynamics picture to have this, because we have compact and closed field lines. So the addition that we need to make to the EM tensor is just essentially this dual where we have everything that's closed and compact being this Hertzian tensor over here. So we can actually draw out the complete multipole family that is applicable to condensed matter under this diality invariant way. And so on the left-hand side, you see the electric dipole, quadrupole, and octopole, the magnetic dipole, quadrupole, octopole, and toroidal dipole, octopole, quadrupole. This is extremely important that we need to get to the third order, because I will show you why in a sec. Let's simplify the problem though. We just have 3 space. We endow 3 space with a scalar charge. If I take the first time derivative of that 3 space, I get velocity. I also get a dipole moment. Second, you can understand, you can follow, I'm getting the acceleration and the quadrupole moment. And if I take a third time derivative, I'm getting the change of acceleration and the octopole moment. The turbulence picture, so some of you might be familiar with the concept of energy cascade. It's the idea that momentum gets exchanged from basically on scale. So it goes from large scale all the way down to tiny scale. So K being the wave number is related to the inverse radius of these compact field lines. But so Kolmogorov, about 10 years previous to his CAM theorem assertion, he actually went and proved that for turbulent flows, it follows this inertial scaling, or this power law, and he derived that. So basically, the idea is that we copy what he did. So what he did was basically take a constant, so a Minkowski space, and perturb it to the second order, look at the units of dissipation, and then how that translates under Lorentzian invariance, and he gets this K to the 5/3 power law. And that works this whole time when you're in the inertial space. When you get to really small radius or high wave number, you get viscous effects starting to dominate, and you go away from the inertial scaling. This is the red line here is the solution to the turbulence problem that I solved. The data is real turbulence data for the longitudinal energy. So if you can imagine, we can take this all the way down to a heat death condition. We can take it all the way down to where there is no longer any energy left in the momentum. And now we need to deal with, well, there is only field interactions in this case. There is only Coulomb interactions. The momentum has stopped, and that is the viscous heat death condition that we want to look at. So Kolmogorov, as I said, looked at the second order perturbations. So we're going to start with a different picture though. We're starting with a constant oscillator and applying this viscous heat death condition of maximum viscosity, and then we're going to perturb that system to the third order. So we're going to look at octopole moments become important, and under the diality expansion, diality invariant expansion, the toroid moments also become important. Okay, we put that under essentially, it's in the handouts that I provided. The first steps was find the irreducible space of de Sitter, the irreducible de Sitter space. The second one, under radial gauge. The second one was define the polarization tensor. And so in order to do that, we just give sigma this property. And then we say, well, actually, let's just put the Pauli matrices and equate them to this. Then we can look at an invariant form of the dissipation. And this is what comes out on the right-hand side. It's a polarization tensor that is the toroid moment, and it's a k to the 6 factor. So remember I said we want to go take this all the way down to basically the 0 density limit. But there's a problem, because if I go all the way down, there's something, if I look in the QED textbooks, it tells me that the vacuum polarization tensor is fixed by the Ward identity. But as a counter to that, I would say to Peskin and Schroeder that, well, actually, the Seagate theorem is implicit in the Ward identity, and the Seagate theorem artificially nulls out the toroid moment, so it's undefined, in fact. The polarization tensor in current QED textbooks is undefined with respect to the toroid moment. This is a big problem. But it's fine if you go from a system where you're in equilibrium and you want to work out some dynamic process and then look at the equilibrium products. But that's not available to us if we want to look at the end state in a turbulent picture. Okay, so long story short is we can actually take this 5-dimensional energy surface. We found the turbulence solution space, but it requires us to choose a polarization. So this is kind of what I've called the stochastic injection. We can give each polarization a weighting probability, and we can iterate through a vacuum fluctuation when it has a completely polarizable, the completely polarizable vacuum. Here's what it looks like. This is the temporal evolution for equal probability weighting. So this would be an isotropic state. We can take the mean value of the absolute value of R, R being in this case related to the Hubble parameter. And because the Sitter space is maximally symmetric, there is only one parameter. It's this parameter, and it is related to the Ricci scalar. Okay, so what comes out is we take this mean value, and then, well, I can change these probability weightings, and I can do the whole spectrum. So for example, up here, if I do sigma 3 of 0.8, this is setting sigma 1 and sigma 2 to 0.1 apiece, okay, for this dot. And you can imagine, so we do the whole space. What comes out, unsurprisingly though, is the weak mixing angle is here at an isotropic state to within the codata uncertainty. But you can see it's also a fairly big cross-section. But this kind of is, it's encouraging to look at this and say, well, actually, if we just start from a turbulent picture, that spin glass picture, apply the turbulent boundary conditions, as in the heat death boundary condition, then what comes out is a spin half representation. I'll give you the geometric interpretation of that is up here. This is a 3-sphere with a radius of sigma, and sigma looks like this. Remember I said sigma is actually the Pauli matrices. So sigma has this SU2 symmetry, and the 3-sphere itself acts transitively on the SU2. So this is a really neat way that we get the spin half generators come out, which we use in QED. All right. So I talked really quickly before, and I will try and hurry up because time's ticking. But this is how shut up and calculate works. You go and look at your system, choose your action, write down your Lagrangian, and then you choose a gauge for your system. But then it's hidden on you because you take that and then you go and calculate your scattering and path integrals, and it's implicit when you do that this transverse gauge is artificially implied on you. And the effect that has is it zeroes out the longitudinal components of the photon. Okay, so there's a couple of fixes, or a couple of ways to fix it. First one is what Klinkhammer suggests is that you actually use a freeform for the gauge. But what we're going to do is just say, well, okay, let's just zero out the transverse gauge, and we're going to look at the radial gauge only. Because remember, we want to look at this vacuum fluctuations, the vacuum turbulence picture. And so we do that, and we get solutions that are U1 cross U1. And this is a U1 of electromagnetism and the U1 of diality. And these are separate things. So the U1 cross U1 solutions are the vortons, which you saw flying around at the start. And credit for those animations goes to Garrod. So he showed in his paper, which is brilliant, and that the winding number, all of these, so 2 gauge couplings, and all of these terms are run, and he found that there are stable solutions and there are dynamically stable solutions for these U1 cross U1 topological solutions. So the ones to remember, though, is the dynamic stability of 6,000 Q value and the stationary Q value of 1,500. And really, if you like, the way to think of it is this big number here is related to how fat and how much charge is carried in these vortons. So if they're sufficiently fat, they're stable. If they have a higher winding number, as you can see from the temporal evolution left to right, that these things will fly apart. Okay, jumping ahead a little bit, we are able to take the solution from the vacuum turbulence picture and plug that into, well, in fact, it's here. So what comes out after we do all the steps in that handout, we get this hypergeometric function, and from that series in the hypergeometric function, we get to make this substitution. Little r is the infinitesimal change in the scalar factor, the scale factor, sorry. And we can put that into the infinitesimal de Sitter path, and then equate that with a whole family of Collis-Klein solutions that exist that have also 2 parameters, so not just black holes, but also solitons. Okay, and we make 1 or 2 more approximations. We put in m here is the singularity radius, so that's the point where nothing can escape. It can only be compact. And then we get, if I plot the infinitesimal paths against each other, the vertical axis here is how much the topological defect has deployed in physical space. So how big is the monopole? And what we can see is that for most of the cases, it is sub-Planckian. Okay, and then I should explain the x-axis is a thermodynamic impulse, and it is the units that you see here. But if we set the inertial density and the charge density to 1, and we just look at perturbations on that, then we can use Hertz squared as a unit of measure. But if you're more inclined to look at the thermodynamics, you can also use those 2. Over on the right-hand side is a legitimate Machian threshold. Here's an interesting tidbit, though. If I get 4 electrons and I spin them in a coherent state, those 4 spin-half particles become a spin-2 particle. And that is a topological defect in and of itself. It may not be at the same energy scale, but it is a topological defect that is sitting on top of the metric. So that's living on the 5-dimensional energy surface. And that lives right up against this Machian threshold. So I thought that's quite interesting. A big part of the motivation of the talk today, though, was being able to explain away why we get so many of these random, or not random, so many of these many nuclide interactions. This is basically reproduced from Maldacena from the Institute of Advanced Study. he looked at magnetic black holes. Remember, this was just the one solution where we've got the 2-parameter solutions. But he looked at the black holes and the condensation or the hypercharged screening that occurs in a macroscopic area around these topological solutions. The problem, though, is that these, like this electroweak condensation or hypercharged screening occurs way up at the mass of the W boson squared. So if you put it into like real terms, that's like 10 to the 20 Tesla. So obviously we're never going to achieve that in the lab. But the motivation for my talk is, well, I'm just going to stick a coefficient on the front, and I want to work out how much of energy budget, how much room is there in the energy budget for me to wiggle down that energy. And actually, what comes out is this is related to how much the metric changes on that 5-dimensional energy surface, but it also is equivalently the dynamic and the static Q values that Gouraud worked out. So if we take the 6,000 value that, for that dynamic stability, then that drops us down to 13 MeV squared. Same for generating an actual magnetic monopole. It's capable of Kalin-Rubikov interactions. The threshold for that would be 20.8 MeV squared. So I should say a little bit on what's actually occurring here. On the top right-hand side, because the Higgs is charged under isospin, we get condensation and changing of the electroweak coupling constant. If you drive it even harder, like thermodynamically, then you get a region of pure hypercharge mixing where there is no Higgs field at all. So remember, we had the 2-parameter solutions. We can look at this C value, which I've got on the left-hand side, versus the whole spectrum of different metrics. And the different lines are looking at integrating out to, from the center, all the way out to a singularity horizon in the blue. And what you see when you expect to look at, well, how much of a discount can I get on the energy required to form these topological defects? It's not a fraction, it's actually, it goes into the negative. So it tells us that not only are these things probably going to be produced, but that they are produced at some level. And that is what I'm saying is the level that we saw on that sub-Planckian scale. Okay, if I integrate out further, I get something that I would assume that, it looks like I get a discount on the energy required. But then somewhere in between, I get a zero energy line, and that tells me that there's this boundary that's significant. So if we zoom into that, this is a log, with just the same graph, but we put a log scale on the left. It's this beautiful, not double potential, but it's a Mexican hat of the metric. So this is a full picture where before Gouraud had this Lagrangian that he put up where he just puts in U1 cross U1. Actually, this was Witten that did this first. U1 cross U1 under the gauge, the radial gauge. But this is the reason why you have 2 gauge coupling constants. I get excited about it. And furthermore, if we set it to Gouraud's value that he found for the dynamic Vorton, then we find that these are 0.8 and 1.2 for the beta values. So now we know which line to look at on this. If beta is 0, this is a Schwarzschild metric. That's a black hole. If we get beta way up to infinity, then that's a pure soliton. But what it tells us is that we're operating at these low beta values is where it likes to be. So we can actually plug in some numbers in a very non-physicsy type of way, but this is like the more of the engineer approach. I just want to see what we can do. Okay, so we'll take the ansatz that the electron has a Q value of the stationary vorton. If we put that in times 4, remember 4 electrons in a coherent state is a topological defect. If we do that, so 4 stationary vortons gives us actually the dynamic vorton Q value. And then if we take 6 keV, plug that into this thermodynamic, the Hertz squared, that's going to tell us, that's going to give me the time constant that I need to spin up some electrons plus, this is the time constant that gives me, so 2 gigahertz, so half a nanosecond, but remember I need to have that polarization, so that the toroidal polarization. If I spin up 4 electrons in half a nanosecond with toroid polarization, that's giving me a spin 2 particle, and that is a topological defect. So we need to be able to explain multinuclide transmutation. Well, we talked about a macroscopic volume around these things that is capable of firstly having changes in the QCD vacuum, then having changes in the QED vacuum, and then ultimately a Kalin-Rubikov baryon violating interaction. And then if this thing gets sucked into that nuclide, remember that the value of the energy was inside is negative. So this is like a reassembly machine, as I'm seeing it. So multinuclide transmutation, yes, I think it ticks the box. Strange tracks, these topological defects are, I'd encourage you to go and read that Gross paper, because it goes through how these things can have inertial mass but no gravitational mass. They can pass through walls, they can have a dipole moment and a monopole moment, or any combination of. So they're extremely interesting in and of themselves. The lack of nuclear markers, I think, is probably one of the more exciting areas, because Kalin-Rubikov interactions, remember we worked out that 20.8 MeV as a threshold. Well, the only nucleus that's capable of holding in a beta minus channel 20.8 MeV is a helium-4, as far as I know. So that's telling me, well, in fact, these topological defects actually would like to hang out inside a helium-4. What would that actually look like, though? We would have baryon violating interactions. It would look like probably a quad neutron or a tetraneutron. When these things, so the Kalin-Rubikov interaction is a proton plus a monopole, and what you get is a positron plus some energy that is not necessarily released, but some of it can be put into like this Z prime vector boson. So, that's an open parameter that we need to find out. I think what we're going to do is look at putting monopoles into lithium-6 and looking at the products. And I believe that we'll get quad neutrons. Okay, the last one is the excess heat or virial coefficient changes. These things are capable of doing that. Remember, they're taking energy from pore space and they're putting it into that fifth energy surface. So that might look like the condensation of the QCD vacuum, where you're putting it into, you're condensing a neutral kaon and charged kaons. Or if you drive it even harder, it might look like what I showed up there before, where you've got condensation of the Higgs vacuum. Here's 2 recommendations. The first one is that topological defects. Remember, we looked at we wanted to work out where heat death occurs. And remember what we found is that actually the thermodynamic Machian limit is the wavelength squared is like the IR wavelength, which I don't think is a coincidence. But what it also should clue us into is if we illuminate the immediate surrounds of your experiment and you're getting strange tracks, or you're getting these anomalous emissivity readings, then illuminate with somewhere in the range of 1 to 6 microns and look for in-band reflectance changes, both in time and space. And the second recommendation is that the collective X-ray phonon modes need only to get up to either 14 MeV or 20.8 MeV if you want to get to a full monopole. But there's a caveat with that, and that is that the ensemble of charge needs to have an appropriate polarization. If we've got time, I've got some extra slides where I can show you an example of looking at possible topological defects under illuminated 1 micron bosons. Anyone want to see it? Okay. If I can work out my tech. Are there any questions in the meantime? While you're coming up, so that's Exifuse. You can get the resources there. You can also look at those 2 papers. The first one's the turbulence from first principles preprint. The second one is the ergodic vacuum preprint.
Yes, I had a question.
Yep.
Why do you consider a spin-2 particle to be a topological defect? I mean, I can understand that it's not at its lowest energy and it may not be stable, but why do you call it a defect?
Because, so I can, there are experiments where we can make analog gravity. This spin-2 particle is a graviton, but not at the same scale. So, I mean, we're talking about a 5-dimensional energy surface, and we're talking about that 5th surface. Remember I said the energy cascade is actually in scale. Moreover, remember that geometric representation I talked about? It's a 3-sphere with a radius of the SU2. That transitive action between the 3-sphere and the SU2, that links chirality with the direction of that energy cascade. So that parallel, is that why we live in a left chiral universe? Because energy is cascading down? I don't know. I just think it's a cool thought.
Why do you call it a graviton then, just because it has a spin?
It's an effective graviton.
Okay, my question. So the point is, you didn't show us what is the probability to product this kind of topological phenomena. So there are some effects which are connected to electrons, not to nuclei. And you need to have this coupling constant between electrons to nuclei. Of course, there is shock waves, everything is okay, but you need nevertheless at least 2 probabilities. One, it is to create this kind of objects, which is not so high, I would say. You need a large energy density for that. Yeah, you didn't say how large energy density is needed for that.
Yeah. Can I answer that question first?
And the second one is what is the coupling to the, to the nuclear or atomic dynamics there?
Okay. So the first question before I lose it is what is? Oh, now I've lost it. Okay, what's the energy required? This is not an energy requirement. This is a change in the power input per volume. So,
but this is also energy change in the power.
Yeah, sure. Yeah, sure. Yeah. That's these values. That's the threshold that you need to get to.
So the question is: it is possible to observe this kind of effects, according to you, in discharge experiments, because they can produce really large energy densities. And as I said already before, this kind of objects have been observed already, in solids, of course.
Yeah, I think my take is that we can do this top left. Mm-hmm. probably more sensitive because you don't necessarily want to just make bulk nuclear radioactive material, although there are some benefits to that. If you can master this, then you can remediate nuclear energy. And if you can master this, you can completely do terraforming and make whatever you want. It's just going to put things into the most stable isotopes possible. This is what this does.
This is the question, about probability. You can have theoretically everything possible.
Sure.
There's probability. How probability is to put the whole energy in the collision?
Yes. So the question you're asking is, what's the cross-section between a monopole and a nucleus? The cross-section, remember I said it's extremely small. We need to provide a whole bunch of power in a volume to try and blow that space-time bubble up, basically, is what's happening. And even if I do, I just get to the Planck length. Remember down here, so 1 over here is still sub-Planckian, so I need to get it up above this red line. So if I'm able to get up here, then it's a very small, extremely small monopole. Kalin-Rubikov interaction is related to the distance, so r to the -6. So very, very, very small interactions. But I guess this was going to be my question to the audience was, would you expect to see any enhanced cross-section when there is a nucleus that has a magnetic moment? It doesn't matter if it's minus, like a negative or positive magnetic moment. But you've got a magnetic monopole. Yeah, Kalin-Rubikov doesn't talk about it, but I believe that you do. Yeah.
Just a quick question regarding these things. The electrons, in fact, in your experiments, do they have some kind of, have you considered the magnetic attraction between them? Because if in its actual circumstances, you should expect magnetic attraction, well, it will depend on their spins. But did you account this magnetic attraction?
No, it's still ongoing. But what does happen in any kind of separation, if you take it to a point not under a high ohmic load, you get this quantized conductance. And I believe that we're getting a similar quantized conductance effect, not fully, but partially on a small temporal domain.
Also, you mentioned that in order you to increase your cross-section, you have to increase the power. Is it actually you to increase the power or to increase the density of the power? How do you think?
Yeah, you look at the units down here. So you could, let's look at volts per charge times meter. So there's, the density of the power. Yes, exactly. Density of the power. Yes.
So, thank you very much. Am I sorry?